Let's discuss how elements of natural language are encoded in deep learning models, and then contrast that with the way these elements are encoded in the traditional machine learning models, TML, that the deep learning models are beginning to outperform and replace. Across this section, notice how the deep learning representations are fluid and flexible, while the traditional machine learning representations are fixed and rigid. Let's start with phonology. So, phonology is concerned with the way that language sounds when it is spoken. Each language has a specific set of phonemes or sounds that make up its words, like pho or neem. In traditional machine learning approaches, the approach was to encode segments of auditory input as specific phonemes from the language's available phonemes. In deep learning, we train a model to predict phonemes, or alternatively full words directly, from features learned from auditory input, and we represent the phonemes as vectors. In these live lessons, we'll be working with natural language in text format only, not audio of speech, so we won't be discussing phonology any further. A language's grammar consists of morphology and syntax. Let's talk about the smaller of these, morphology, first. Morphology is concerned with the forms of words. Each language has a specific set of morphemes, which are the smallest units of language that contain some meaning. For example, the three morphemes out plus go plus ing combine to form outgoing. In traditional machine learning, morphemes were identified in text from a list of all the morphemes in a given language. In deep learning, we train a model to predict the occurrence of morphemes. Neural nets can combine multiple vectors, e.g. out, go, ing, into a single vector representing a word. Let's move on to words. So words are the level of natural language that we'll focus on in these live lessons. We'll focus on words partly because it's easy to define what a word is, partly because it's easy to break up natural language into words through a process called tokenization. And in this tokenization, we assume things like commas, periods, and white space are natural indicators of where one word stops and the next one begins. And then we turn all of those words into tokens. And partly we focus on words because this is the most studied level of natural language with respect to deep learning, so we can apply cutting-edge techniques to words readily. In traditional machine learning, one-hot representations of words are the norm. So I'll quickly explain what that means. If we take this sentence, the cat sat on the mat, and we wanted to one-hot encode this sentence, then we would have a row in a matrix that represents the, and then we'd have ones indicating where those are, and zeros everywhere else. And we continue that throughout all of the words in the vocabulary, in the corpus. So cat gets a 1 here. And you can see that as the vocabulary gets larger, the more unique words we have, this matrix becomes very, very large with a lot of zeros. So this is called a localist approach, and it doesn't capture that highly related words like hotel and motel are in any way similar. They're completely distinct local concepts. In deep learning, on the other hand, surprise, surprise, we use vectors again here. And with vectors, we can represent all of the words in our corpus of language in an n-dimensional space. So here I've drawn a three-dimensional space for you. In a moment, later in these live lessons, we'll be putting words into an n-dimensional space. Because our brains really only work with 3 dimensions or less, I've just drawn this box here. In the real world, we will have much larger spaces. But the way that this works in general is that more similar words, like common spelling mistakes, will show up in the precise same place within this n-dimensional space. And then slightly less related words like hotel and motel will appear further apart from each other, and so on. Later on in these live lessons, we'll get into this concept in detail. You'll be making your own. And at that point, this whole idea will be very clear intuitively. The subsequent lessons in these live lessons after that will build on that understanding of word vectors to build functional, efficient models for performing natural language processing tasks. Let's move on to number 4, syntax. Syntax, alongside the morphology described earlier, constitute the entirety of a language's grammar. Syntax is the arrangement of words into phrases and phrases into sentences in order to convey meaning in a way that is consistent across the users of a particular language. In the traditional machine learning approach, phrases were bucketed into discrete formal linguistic categories like noun phrase or verb phrase. In the deep learning approach, guess what? Vectors again. So in the deep learning approach, every word and every phrase in a section of text can be represented by a vector in an n-dimensional space. Neural networks can then combine those words in the n-dimensional space into phrases. Finally, the final representation of language that we'll talk about is semantics. So semantics is concerned with the actual meaning of sentences. Meaning is inferred from all the underlying language elements, like its words and its phrases, as well as the overarching context that a piece of text appears in. Figuring out meaning can be tricky because, for example, whether a passage is supposed to be taken literally or as a humorous, sarcastic remark can depend on subtle differences. In the traditional machine learning approach, this required carefully engineered lambda calculus functions. Ultimately, this was a limited approach because it doesn't capture the fuzziness of language, for example, the similarity of related words or phrases. In deep learning, guess what? We have vectors again. And in deep learning, vectors come to the rescue here again because vectors can represent every word, every phrase, and every logical expression within a passage of text. As in the language elements covered above, neural networks can combine the underlying elements, the words, the phrases, so that here semantic vectors can be created by neural networks combining those phrase vectors and word vectors together. Perfect. Those are the 5 levels of natural language elements, as well as the limits of traditional machine learning approaches for encoding them, and the near magical flexibility of vectors for representing them instead with deep learning models. Up next, we'll have a peek at some powerful applications of vector space leveraging deep learning models to NLP tasks.